Welcome to your identifying and combining forces homework. Number 1, can an object move if the net force is 0? Now the word here that we look is move, not accelerate. Since move, yes, you can move. So the answer is yes. And the explanation would be, as long as the object is not accelerating, it can move. It's important to understand that a force is not required to make an object move. A force is required to make an object accelerate. Number 2, can an object accelerate if the net force is 0? So if the net force, the sum of the forces equals 0, then that means it cannot move. Nope, not at all. It only accelerates if there is an overall net force on it. Can an object remain still if the net force is not 0? Nope. If there is a net force acting on an object, it is going to accelerate. That is the message here, folks. Net force equals 0, the object does not accelerate. It can move but not accelerate. But if the net force is not 0, that means there is a net force, the object must accelerate. Can an object slow down if the net force is positive? Yes, it can. Remember, a positive force causes a positive acceleration. And a positive acceleration means either speeding up in the positive direction or slowing down in the negative direction. Number 5, can an object move at a constant velocity if the net force is not 0? And the answer is no. Because if the object is traveling at a constant speed, there is no force acting on it. If there is a force acting on it, it must accelerate. So you cannot move at a constant velocity if the net force is not 0. Sorry for like that. Well, I guess there's no double negative there, is there? Let's look at our next section. Which of the objects shown above has a negative acceleration? So all you have to do to find the acceleration, whether it's positive or negative, is simply look at the direction of the net force. In this case of A, there's only one force and it is acting in a negative direction, therefore the object is going to have a negative acceleration. The direction of the force vector is the direction of the acceleration vector. So in this case the answer is A. Which of the objects shown above is not accelerating? Now, they all have forces acting on them, but if we look at C, it has a force of 12 newtons in the positive direction and 12 newtons in the negative direction, and those two will cancel each other out because we always add forces. So positive 12 and negative 12 equals 0, so therefore the answer to that one would be B. The net force is 0, so it does not accelerate. Number 8, which of the objects shown above has a positive acceleration? Well, that would be B, and here's why. What you'll notice is the negative force is 12 and the positive force is 18. So when I combine positive 18 and negative 12, that leaves me with positive 6. So it's going to have a positive acceleration. Which of the objects above is speeding up? The one that is speeding up is the one with the negative acceleration. And I did that on purpose because I want you to understand that a negative acceleration does not mean you're slowing down. It means that you're accelerating in the negative direction. And the correct answer here is A, because it's moving in the negative direction and the force acting on it is going to make it pick up speed in the negative direction. So to go faster in the negative direction is a negative acceleration. Which of the objects shown above is in static equilibrium? Now, static equilibrium means that's the key word to look at here. Static. Equilibrium means the sum of the forces equals 0. And the object is not accelerating. Now that applies to C, except C is moving at 22 meters per second. That's called dynamic equilibrium, not static equilibrium. So the answer is none of these. And therefore, the next one, which one of these is in dynamic equilibrium? That would be C. Because in the case of C, the sum of the forces equals 0, so it's not accelerating, but it is in constant motion. Alright, we're going to be a little bit careful with number 12 here, so let's see what we have. We have the force of tension acting this way. Ft tells me it's tension. There's a rope pulling it this way, and this little f means this is the force of friction. Now friction always opposes motion, so I know that this force is oriented in this direction. Now at this point we don't know the magnitudes of the forces, so we don't know if this object is accelerating or is in static or dynamic equilibrium. So let's read what it has to say. The object above is moving to the right at a constant velocity. Since it's traveling at a constant velocity and there are two forces acting on it, it must be in dynamic equilibrium because otherwise it wouldn't be at a constant velocity. And that means that the magnitude of this force and this force must be the same, otherwise it would have to accelerate. So therefore, in this case, neither force is greater. It is in dynamic equilibrium. If the object above is slowing down, so if the object is slowing down, but keep in mind it's moving to the right, but it's slowing down, that means it's experiencing a negative acceleration. It's slowing down on its way to the right, which means that this force must be greater than this force. So therefore, the force that is greater is friction, because it's causing a negative acceleration on the system. People write AP questions, love this type of question. All right, the diagram above shows a stack of books, my lovely books here. The books are not moving, so they're not falling down or anything like that. What is the normal force acting between them? Remember, the normal force is the force that acts perpendicular to a surface. So I actually have 1, 2, 3 surfaces in question here. So it says, what is the normal force acting between books A and B? Well, since book A is not moving, it must be in static equilibrium, and therefore, since the weight of the book is in the downward direction, there must be an upward force of 3 newtons acting, a normal force of 3 newtons acting in the upwards direction. Now between B and C, I have my system is now 2 books that are being pulled downwards. So you can look at it this way. I have 3 newtons pushing down on this one, which weighs 8 newtons, so I have a combined force now of 11 newtons. So I'll just write that here. Right now I have 11 newtons of downward force. And since the system is not moving, it's in static equilibrium, I must also have 11 newtons of upward force, and that would be called the normal force. So the answer now is 11 newtons. And then what is the normal force? That is the force perpendicular to the surface, which in this case is upwards. If I stack all of them together, so I simply say, well, I have 3, which is pushing down on 8, which is pushing down on 5. So I have a total, in this case, of 16 newtons of downwards force caused by gravity. And the table surface here is pushing up on the system, keeping it from accelerating. So it must also be pushing up with a normal force of 16 newtons. So in a problem like this, really all you have to do is add the weights of the books and then have that go in the opposite direction. The diagram above shows a stationary box. So I know that this box is in static equilibrium and the sum of the forces equals zeros. The box is being lifted by a rope which is applying a tension to it of 12 newtons. What is the magnitude of the normal force? So I have 3 forces acting here. Gravity is pulling it downwards with 26 newtons. The rope is applying an upward tension force of 12 newtons. Now, since the system is in static equilibrium, it's not moving. The sum of the forces must equal 0. There is another force involved here, and the other force that is involved is the normal force, which in this case must equal, it must be an upward force of 14 newtons. And the reason is, my upward forces, tension and normal, must equal the sum of my downward forces, which in this case is just friction. So 12 up and 14 up gives me 26 up, and that will put the system into static equilibrium if the downward force is 26. The diagram above, well, I had to read that one, okay. The diagram above shows a box weighing 26 newtons, that's downwards. You always weigh in the downward direction towards the center of the earth. That is supported by a rope that is applying an upward force of 12. So it's just like the one above, except look, there's no floor. What is the net force acting on the box? Well, in this case, the net force is 14 newtons in a downward direction. Which way is the box accelerating? It's accelerating downward, because the net force is in the downward direction. And finally, number 17, the diagram below shows a box that is moving downward at a constant velocity. It is not accelerating. If the velocity is constant, That means there's no acceleration. We are in equilibrium, in this case dynamic equilibrium. And when things are in equilibrium, what is the sum of the forces equal? 0. So therefore, I know that the weight of the box must be, first of all, let me point out, you can totally ignore the fact it doesn't matter what velocity it's traveling at. Since it is not accelerating, the sum of the forces must equal 0. So therefore, the force of gravity acting downward on this box must equal 25 newtons in a downward direction. I hope you like that. I love this stuff.